Welcome to today's webinar. The topic today is load capacity analysis of systems for maximum resistance. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today, and I will answer your questions during the webinar. My colleague Ulrich Lex will be the presenter. He's responsible for the development of Forme, especially for the add-ons masonry design, glass design, and construction stages analysis. Yeah, and I wish you that you enjoy the webinar. Okay, then I say something how you can ask questions. At first, I switch off my webcam that you can see the full screen. Just press the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Ulrich. Ulrich, it's your turn.
Thank you, Andreas, for your introduction, and also hello from my side to today's webinar. The topic of today's webinar is load capacity increase using structure stability add-on in Forme 6. I want to show you to use a linear and a non-linear material for this job. As a second part, I prepared two other examples to show you all the possibilities what you have with this add-on. So on this part, I want to switch to the program and start with the system. The system I've prepared is quite easy. It's one surface with a height or length from 3 meters and the width of 1 meter. It's created in material glass, but the material itself does not have any special things. So it doesn't matter if it's a glass, if it's concrete, if it's steel. It's always the same behavior. So take a look at the base data. Today I have activated the add-ons for nonlinear material, the add-on nonlinear material behavior, the structure stability, and for design, the glass design, because it's created in material glass. So what want I to do today? I have this system supported in the upper line and downside, and I have two different load cases. One load I created as a permanent load. It's located in the upper line, and the other load is a horizontal load, maybe from people or anything else. So, and what I want to do today is to look how big, how much can I increase the load so that this system is the system I'm able to compute that the stability is given for this system. Here I can easily use the add-on structure stability. So one time shot back to the theory. Because we can do this also in the theory. I can compute here my critical buckling load, maybe also with formulas. As I told you, the system, the height is or length is 3 meters, the width is 1 meter, the thickness of the surface is 12 millimeters. Material is glass, and the E-module is 70,000 Newton per square millimeters. So when we take a look on the formulas, we can here use the Euler formula. It's called FK P square multiplied with the E-module and the buckling length. The buckling length in our case, it's a pendulum. It's the case 2, where the buckling length is equals the length of the system. So when we fill the values in the formula, we get a theoretical critical buckling load of 1105 kilonewton. This can be easy check with Forme 2. So go back to the program. How can we do the settings? So if the stability analyze is checked on in the base data, then you get a new entry in load cases and combinations for the stability analyze settings. Here you can find these settings. You can also assign it directly to a load case or even to a load combination. It's possible for all load cases and combinations. Here I can check on the structure stability add-on and can create new settings for it. When I continue to create a new setting, here I have the possibility to use different analysis types. On the one side, the eigenvalue method, or for nonlinear things, the incremental method with eigenvalue analyze or without eigenvalue analyze. So in the first step, I want to use this eigenvalue method. And here I have the settings, the possibility to use different methods. You can find in the manual what is the best setting. So this is all what I have to do in the settings. I can continue with OK. I want to use the permanent loads. It's without self-void, even that I can compare it better with my analytical solution. If we have checked on the check, we can calculate the first load case. So you see in the calculation dialog that at first the load case is computed, and as a second step the stability analyze is done. You find the results are not here in the dialog on the upper side. You find the results on the navigator, one time the static analyze results, and if you click, you can choose the stability analyze results. The same is in the result table. Here you have the results for static analyze and stability analyze. So when we take a look on the results, we find critical load factors. The critical load factor means the factor how much I can increase the given load until the system gets unstable. In our case, the first critical load factor is 22.264, and with this factor, I want to switch to my PowerPoint. So manually, we computed 1105 kilonewton. What does FM do? With FM, we computed a critical load factor of 22.264. Our load was 0.5. That means I get a critical load, a critical buckling load of 11.13 kilonewton. So we see it's nearly the same as, or it is the same as the formulas. And in this way, we can check the results of RFM 2. Okay. So the load itself, we can also show when we I show you even later the support reactions. Okay. Now we have done the eigenvalue. So as the second part, I can increase this load because I want to know how much I can increase my load with the vertical load and the horizontal load. How can I do this? Before I do this, one topic I use here for the Analyze settings, the large deformation calculation, because it's a special thing for glass, because for the large deformation analyze, there are some membrane stiffness of the surfaces activated. This is important for thin surfaces, for surfaces with are acting more as a bending. With bending, it's not so important, but here it's important to get the system stable, because here are the normal forces are acting also for the bending moment. You have to know it, because when we increase now the load for the horizontal and the vertical situation, then it happens that the system gets big normal forces, and it's caused by the large deformation analyze. So okay, when we now want to take a look at both load cases, we create a new load combination. I use here also large deformation analyze. I assign my permanent loads and my horizontal load. I can check on the structure stability. I want to use now an incremental load method. an incremental load record. I want to increase my load. The settings are the initial factor is this factor or this load, what the stability add-on is starting with it, and the increment is how the steps who are increased in each calculation. So I can here start with factor 1 and the increment could be 0.5. And the maximum number of increments is only the thing where I can say how long should the add-on compute until it stops. So even the refinement of the last step is when the program find the maximum load, then it goes one step back and do the steps with the refinement to get better results or more exact results. One important option is here on the right side. You can save the results for all increments. If you check off this or do not check on this setting, then you get only the last load step. And if you have checked on, then you can take a look on each load steps the program computes. So with this setting, I can continue with OK. OK, and can compute my load combination. Now I using a linear elastic material and use both loads. So as I said before, the static analyze is done, and as a second part, the stability analyze. Here you can even show or even take a look at the deformation in each increment and can take a look on the calculation. Okay, we see the displacement gets higher and higher, and this is what I told before. It's because of the large deformation analysis is activated, because now the system is, because of the horizontal load is bending, and the normal the membrane forces are acting. So this system is acting as for tension and not for bending. This is a special thing for glass structures. It would not happen when the thickness of the surface is bigger. So now the calculation stops, and we will take a look at the results. So we can see that the calculation stops with 100 in the increment 150. We get here a message that the load factor, that this is the load factor when the maximum number of increment is reached. This is what the setting from before. The program computes until this load increments. That means that the results are not, that the calculation is not really ready, because if I allow more increments, then the program will compute more increments. For our case, it's okay here, because when I take a look at the results at the maybe deformation in increment 150, I have about 3 meters deformation. So it's not usable in this case. But what I want to show you is now on the stresses of the surface. So I can take a look on the principal stresses, maybe sigma 1. So the special thing of glass is, or of this glass, I know that the allowable stress is about 80 Newton per square millimeters for a thermally touched float glass. So now I can take a look at the stresses in each load case. So that means I can scroll down and see my maximum stress is 80. So I can maybe, I'm here on 6.56. Here at the load step 4.5. Load step 4.5, I reached a maximum stress of 80 Newton per square millimeters. And now I can take a look at the support reactions. We will see that when I take a look on the resultant, then we can see that the vertical load and the horizontal load are increased in the same way. So my original load 0.5 and the load factor 4.5 is the vertical load of 2.25 kilonewtons. So now I can do a simple check. I can create a glass surface. Maybe new thickness. As in glass. I'm using the same thickness. It's only to be able to can design it. I create a new load combination with the load factor 4.5. Okay. Okay, and now I can design this structure with the load of 4.5. When we are right, then we should have an I did the stability analyze again. It's not needed. But okay, I can stop it here. Yes. Okay, and deactivate it. Okay. And run the calculation again. Then it's no stability analyze done. So when we are now ready, when our doing was ready, correct, then we see that the design is nearly 100%, the design ratio. So this is an easy way to find a way how much I can increase the load for this system. So now we increased the horizontal and the vertical loads in the same way. This is maybe not the case, or not needed for each time. Maybe it's needed that I only increase the vertical load, or only I increase the horizontal load, and this also can be done with the add-on. The second part I want to change is the nonlinear material behavior. So I want to start with the nonlinear material behavior. I assign at first my thickness of 12 millimeters and use the nonlinear material. For the nonlinear material, I created also a material type class. I use the isotropic plastic material model, and I used the stress failure hypothesis of Drucker-Prager. It's because the most known thing would be von Mises. Von Mises, I can set only one value for strength and compression, for tension and compression strength. Drucker-Prager, I can define two different values for compression and tension. The glass material has a very high compression yield strength, so I set 300, and for the tension, as I said before, I used this 80 Newton per square millimeters, what I took a look before too. So when I define this and use now the stability analyze, then following is happen. The add-on increases the load until this point where the 80 Newton per square millimeters of the strength is reached, and then the calculation is stopped. Of course, we have now to think about it. If my material is really a plastic behavior, or not. So you have really to focus on it. But I think it's a good way to get a feeling how much I can increase my load. So I want to do it in the same way. I have here I can do it a little bit finer, I would say. Okay, and now the settings are done. So as a second step, I want to show you is that I only want to increase my vertical load, and I want to have my horizontal load in the same I want to have it fixed. So I can do it in this way when I use the initial state. Here I have to say, okay, I use here now load case 1 and load case 2, and as my initial state should load case 2 acting. That means my load case 2 is always on the same level, and I increase only my load case 1. You have to be careful because the load case 2 used here for initial state has to be the same as the assigned load case. When I use here maybe any load factor, then I would have to create a new maybe load combination, load case, a load combination where I have this load factor here too. But in our case, I use 1.0, so it's okay. So what happens when I now compute these things? In the calculation dialog, you see now it's at first the load case 2 is computed, then the combination, the static analyze for load case 2, the static analyze for the combination, and after that the stability analyze of the combination 1 is done. So now we see the calculation is running and the calculation stops before our 150 increments. So now the calculation stops at about a load factor of 20, and when we check the stresses, then it is exactly the stress we have set. Here the stress is 80, is a little bit higher because the nonlinear behavior or the setting is from it's used equivalent stresses for checking the results, so it's a little bit higher. But I think for that what we want to do, it's enough. So now, what does this result say? The results say, okay, we can increase the load about 20 times before the system before a collapse of the system is given. When we take now a look on the support reactions, we can see that the horizontal load is the same with 0.5, and only our vertical load is increased about this 10 times. So this is a possibility. You can check how much you can increase this load. The same you can do in the same way for the horizontal load. You can say, okay, my vertical load is fixed, and I only want to increase my horizontal load until the system is unstable. So as a last step, I want to take a look at the deformations. So the stresses maybe would be okay for a design, but the deformations are about 190 millimeters. It's quite high, I think. So what can we do in the stability? add-on, we can say, okay, stop the calculation when a wished high of displacement is reached. So we have here a length of maybe 3 meters. When I say, okay, 3000 divided to 100, it's about 30 millimeters, where I can allow the deformations. So, and this setting we can do in the same way here for increasing loads. We can activate the stopping of load increasing. We can use here the deformation, the deformation in the different directions. And we can define a value. Maybe I define here 30 millimeters and can say, okay, I can say that one exact node have this deformation, or I can say the whole system, the maximum deformation of the whole system is not bigger than this value. When I continue with OK, we can see that the calculation is running and the calculation should stop for 30 millimeters. So when I take a look on the results, I see that my load factor is 4.4. Here I get a deformation of maximum 30 millimeters. And my stresses are even smaller. So with these settings, you can find out how much the load increasing can be done. So now I want to stop here and I want to switch to a second example I've prepared. It's an analyze of a section, of a T section. This T section is created as a surface, as two surfaces. A special thing of these sections are these openings, these holes. And here I want to do a design and also a stability check for it. So what we have to do, we have on the one side the loads, a permanent load, and in this case a snow load. Now I can also activate here a stability analyze, and I want to analyze or to get also the eigenvalue method with the same settings as before or with the default settings, and can compute this eigenvalue for this cross section. So what are the results now? For the results I get now also the critical load factors, and I get the different eigenforms for these systems. When we take a look on the second eigenform, it's a buckling on the second part. The first eigenform is the buckling on the first part, and so on. So this eigenform can we now use for a design of this section. When we want to design the load combination, then we can do it here. We can here consider an imperfection. We have to create a new imperfection. We have to choose here maybe the buckling mode. I want to select a load case. I want to use the buckling mode from load case 1. And here, as we took a look before, the buckling mode, the eigenform 1 we want to use. Here I have to say how the scaling of the imperfection. I can to say, okay, it's in direction of the eigenform, and I want to define a high of the imperfection. That means when I go back to my load case 1, I got this eigenform, and I say now for load combination 1, he should use this form as an imperfection, and the value of 3 centimeters, 30 millimeters, should be here on this point. And the rest of the points are scaling automatically. So when I did these settings, I can compute the combination again. And we see at the deformation that this curve of the imperfection is used or is assigned. Short for compare the things, I can create a second combination where I do not use the imperfection. Here I get much lower deformations and much lower stresses. So exactly here you have the perfect form. And in the first case, you can consider easily these local imperfections for the system. So this is a good point how you can use this at stability analyze. As the third part, I want to show you is something for members. I created here an steel hall with loading of permanent loading and imposed loading and so on. So, but my problem now is that I get an instability when I compute even the permanent loading. So this can be happen when I have a bigger modeling to do a bigger modeling and so on. I get this error message. Okay, the calculation says, okay, stiffness matrix is singular, it's unstable on this point. When I take a look on this point, it seems everything is okay. Here I have maybe hinges. It's a member type beam, okay, with hinges, but the hinges is around Z and Y, so it should be okay. And for this case, I can use also the stability add-on. I can here create a new setting where I say, okay, I use the eigenvalue method and I want to calculate it without loading to check the mode shape. When I check on this and run the calculation again, then I get results for an geometric instability of the system. I would say for this easy system, I can find, or it's more easy to find the instability. When the system will be bigger and bigger, so it's more difficult. And here is this option very good, because now I see, okay, on this point, there is the instability. It looks like that this member is not connected to my column, and I can check it afterwards. I can check it when I scroll in, and I see, okay, my nodes are not connected. Here I have a gap about 1 centimeter. And this is the reason for this, so the instability. So I can connect it easily, and after that the calculation is running. So what can I do now? I can here check off it, because now the calculation is running. So here we have the option to define the number of lowest eigenvalues. Sometimes it's needed to increase this value. The default setting is 4. Sometimes it's needed, and we can see what happens when we increase it. I can compute it. Then the number of more eigenvalues is computed. And we see it's sometimes important, because sometimes we have some local eigenforms for local members, I would say, and the second eigenform would be maybe a global eigenform for this system in x direction, and the third eigenform would be maybe a global in y direction. And when I want to look at any different member, I would say I have to take a look at other eigenforms. These values I can use also for as buckling lengths, maybe to design the separate members and so on. So for this case, it is sensible to increase this number of eigenforms. So in this way, this would be all I want to show you today. I want to say thank you for listening. Hopefully you enjoyed it. And I want to give back to Andreas.
Thank you, Ulrich, for your presentation. I have an additional hint for you. You can book our online courses. For example, the RFM6 course, it's a course for beginners. Then the Eurocode 2 course for the concrete design with RFM6. Then the Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. And the Eurocode 8 course for the earthquake design. For more information and prices, just scan the QR codes, or you can click at the links here. You can download the slides from the same page where you can find the recording. The next days you will get an email with a link to that page. You can get such a course, such an online course for free if you submit a customer project, and after publishing, you will get the voucher for such a course. Now just scan the QR code or click the link here and submit your project. You can also write me an email to info@dlubal.com and I will answer you and write what I need for documents and files. It's not much work for you, I promise. Then I can recommend our free online services, for example, the Dlubal community, where are already a lot of members. You can ask questions there, for example, and our team or other users will answer you. Feel free to join the Dlubal community. Then the GeoZone tool, it's for the determination of wind, snow, and earthquake loads. The cross-section properties, you can download models, for example, as template for your project. If you don't have our programs, just download the 90-day trial version. RFM6 and RStab 9 contain all the add-ons without restrictions. Just scan the QR code. You can also explore all our services when you click at the link here or scan the QR code. More information can you find on our website, dlubal.com. For example, the knowledge base articles. You can ask our AI assistant Mia 24/7 and she will answer you. Okay, that should be also all from my side. I thank you for your attention. Thanks again to Ulrich for the presentation. I wish you all a nice rest of the day. Bye-bye.